And here we are for part two. Actually, since recording part one, I trimmed this down slightly to try to make it a little less longer, so hopefully I succeeded. I suppose we will find out soon. Cool, let's get to it. So I said the big theme of this one would be rotations, and that is absolutely true. Before we do rotations, though, I do want to show the scaling matrix because I mentioned this, I described it last time, but I didn't show what it looks like written out. And this is going to be our first application, really, of the identity matrix. I know I kind of brought it up as like well, hey, what's the inverse of a matrix? It's the thing that when you multiply it by the matrix, you get the identity. And so that sort of required us to define the identity matrix as well. That's all true, but we can go further with this now. So if we want to take a very broken animation just like this, I'm not sure what just happened, but we want to take a vector x. So I'm going to do my examples in 3 dimensions for now. So x, y, z are its components. And we want to make all of those components larger by the same factor. That's what a pure scaling operation is. Like if I wanted to just triple the size of the whole thing, then I would just have 3, 0, 0, 0, 3, 0, 0, 0, 3 as my matrix elements. And so then that would lead me, when I do the multiplication, to get 3x and 3y and 3z as the new vector. And you can see that this gives us a reason structurally to use the identity matrix in writing out this action, because the identity matrix was ones on the diagonal and zeros everywhere else. This also now gives another way to define what the identity matrix is, which is it is the matrix that represents the transformation of not doing anything, which I guess sounds a little boring when I put it that way. And it's by analogy to the number 1. The number 1 is the number that when you multiply it by something else doesn't change it. That's really what it is at the end of the day. And so the identity matrix behaves similarly. Why don't we just write this as the scalar a times the vector x? And the answer is, in this isolated context, you can, and it really makes no difference at all. However, when we start doing more complicated transformations, like in the very next slide or two, when we are using transformations that require multiple steps, where we are doing actions in sequence with each other, we are going to want to build those complicated transformations out of simpler parts. And if part of that transformation is a scaling step, then you'll want to write that as a matrix of A times the identity matrix in your sequence of matrices that you're doing to build the whole transformation. And within the next few videos, there will be another place where we have something that just kind of looks like a scalar, but writing it as a scalar times the identity matrix will give us ways to combine it with matrices in equations that have multiple pieces to them. So we're building up that habit now. Okay, that was scaling. Now on to rotations, which is going to be what we spend most of the rest of this video on. The rotation matrix. And I have isolated the here, just kind of like the exponential function or the logarithm, very much in that same spirit. The rotation matrix, of course, is not the only possible rotation matrix that exists. But when I say the rotation matrix, I mean this one in 2 dimensions. So I'm talking about rotating shapes within the plane. And the components are this. You can see it here. If you just stop and stare at this for a minute and don't overthink it, I feel like it really does kind of make sense. You're like, oh yeah, I have some X's and Y's and I have sines and cosines, and like that checks out. And then if I'm rotating something, then I start mixing X's and Y's together, and each of them has a different amount. And that amount depends on the angle of the rotation. So the exact derivation of exactly why is it cosine here, why is it negative sine there, it's a little bit fussy. It's also not super interesting. It's just being really careful with trigonometry, so I'm not going to derive it here, but I hope it does seem reasonable just looking at what the elements of this matrix are. Now, what's a little bit less obvious is extending this to higher dimensions. Oh, I forgot to say an important thing. Good work, slide, for reminding me. The theta here, this angle is an angle in the anti-clockwise direction. So by default, hopefully you remember this from Math 215, but if you don't, that's okay. The positive direction for angles is anti-clockwise or counterclockwise. And the reason that that is the positive direction is, and I'm like gesturing with my hands here as if you can see it. If you think about our coordinate system, our XYZ coordinate system, that is a right-handed coordinate system. If you take actually do this, like obviously I can't see you, but do it, play along at home, have a little XYZ coordinate system. Point your fingers of your right hand along the x-axis, and then curl your fingers toward the y-axis. What's going to happen is that your thumb points up in the direction of the positive z-axis, and your fingers just rotated through an anti-clockwise angle, a positive angle, and that positive angle corresponds to this rotation around the positive z-axis. A right-handed rotation around the positive z-axis is a positive angle. Why is right-handed positive? Obviously, it's because right-handed people have dominated the world and imposed their values on the rest of. Okay, it's a cultural problem. All right, so positive angle, anti-clockwise. Now, to go up to 3 dimensions, if we're rotating around one of our coordinate axes, it's not so bad because that component stays constant. If we're rotating around the z-axis, for example, the z component does not change. The x's and y's change around the z, but the z itself is fixed because that is the axis of rotation. And so these zeros and 1 in this matrix, those are the ones that are going to involve the z coordinate when we multiply this out by the vector xyz. So you can see that will isolate z, keep it unchanged by itself. It'll be z times 1 in the bottom right corner, and then x and y will change. There are analogous matrices for rotating around the x and y axes, and the x-axis has the 1 in the upper left corner. So it goes like 1, 0, 0, 1, 0, 0, and then cos minus sine, sine, cos. The y-axis one is a little bit funky. I actually revisited my notes from last year to decide how I felt about this and whether I could explain it better this year. Maybe I can. I'm going to try. For the rotation around the y-axis, what the matrix is going to look like is that it'll be cosine in the top left corner, cosine in the bottom right corner. The top right corner will be positive sine, and the bottom left corner will be negative sine. Now, if you look carefully at the z rotation matrix that's written here, you'll see that the positive or negative, the SIGN on the top right and bottom left sine, SIN, actions has reversed. Why does that happen? Well, let me point out another couple of examples where the y coordinate, the second coordinate really, picks up this negative sign. One is in determinants. I know several of you have done 3x3 determinants with this process of taking a matrix and crossing out rows and columns and getting reduced matrices and doing their determinants. And that's a completely fine method. It works. And when you do that, you have to remember to put a negative sign on the second component of that determinant calculation. It's the same negative sign here. Another example is when we are doing cross products, which were briefly mentioned earlier this semester. when you think about the cross product, then there's also this negative sign that shows up in the second component. And that pattern repeats in other places as well. A lot of these uh, vector and matrix entities that we work with, fundamentally, there's this underlying sign SIGN alternation thing where you have plus minus in the calculations as you alternate between coordinates, and that's showing up here as well. All right. There is actually more to it. There are deeper layers to that particular onion, but that's enough for now. I don't want to get too far away because I want to show a couple of specific examples in this video. So first example, I want to start simple and just do a 90-degree rotation in 2 dimensions. That might seem a little bit boring, but there's actually something very interesting, borderline weird, that's going to come out of it. So let's see where this takes us. First, we'll say, okay, we want a 90-degree rotation. Let's write the, in quotes, I hope you heard the quotation marks. So we'll write the rotation matrix. In the plane, 90 degrees. So cos, negative sign, sine cos. That'll be 0, -1, 1, 0. So now sorry, I skipped a step. This matrix, 0, -1, 1, 0, that is a 90-degree anti-clockwise, right? Because this is a positive 90-degree rotation. So that acting on any vector will take that vector and rotate it 90 degrees. So then if we did this twice, then it should rotate things 180 degrees, right? Which it absolutely does. And the way that you do sequential transformations is to multiply the matrices in sequence. So let's square the rotation matrix. We're going to have this matrix times itself. And when you do the multiplication, and you do it very carefully, and I actually really confused myself for a second when I was laying this out because I didn't do it with my nice put things on the page where I want them method. I tried to go through it with without that crutch, and I struggled. Anyway, in the top left, we'll have -1 times 1, and so we get -1. In the top right, we have zeros. In the bottom left, we have zeros. And then in the bottom right, we will have +1 times -1. And so that gives us -1 in the bottom right as well. And so this matrix, -1, -1, in the top left, bottom right, zeros off diagonal, that is negative the identity matrix. And so our identity matrix has shown up again. It's going to keep showing up as we keep doing more things. And this is going to then imply something really interesting and maybe a little bit weird. You can raise a matrix to an integer power very easily. You just, if I have a matrix cubed, it's that matrix times itself times itself. What about non-integer powers? Can I take the square root of a matrix? Can I do a matrix to the 1/2 power? Well, depending on how you define things, maybe. And I'm talking about square matrices specifically here. So what would the square root of a matrix be? Well, it would be the matrix that, when multiplied by itself, gives you whatever answer you're looking for, the thing that you want the square root of. Well, if this rotation matrix squared times itself is negative the identity matrix, then if I take the square root of both sides of the equation, wouldn't that kind of imply that the square root of negative the identity matrix is a 90-degree rotation? And you're like, this is starting to get weird and I don't like it. Well, you should like it, and it is weird. The identity matrix, remember, is our matrix analog of the number 1, the scalar 1. So negative identity matrix is kind of like -1. And so now we're talking about the square root of -1. And I see where this is going. And I hope you see what I did there. So is Is a 90-degree rotation the number I? Well, kind of. If we draw our complex plane here, so we've got a real axis and an imaginary axis, if I, that one was unintentional, that was just a pronoun. If your humble teacher, in this case, takes a point on the real axis and then rotates it 90 degrees, where does it land? It lands on the imaginary axis. That 90-degree rotation multiplied the number by square root of -1. So there's a very good analogy here. And this is not a coincidence. It's not an accident. This is actually very meaningful. There are a lot of correspondences between 2 by 2 matrices and complex numbers. In fact, there's a family, a class, a set. I'm not actually remembering what the correct mathematical term is, but I'll say there's a family of 2 by 2 matrices that have identical properties to complex numbers, that they follow the same rules for multiplication and addition and subtraction and exponentiation and all that. I want to say isomorphism. I don't know where that's coming from. That's some very deep memory and maybe wrong. But I think you call this group of matrices an isomorphism of the complex numbers. Okay, time to move on. Long story short, rotations, complex numbers, very intimately related. We'll see more of this later this semester. Okay. I am now going to just introduce a couple of vocabulary words. I'm also going to say upfront very transparently, many people find this confusing, especially the first time they learn it. I still occasionally get myself twisted around with this. So I am not saying this for the sake of you learning and mastering it and just being perfect at it right away. Completely the opposite. I'm saying I'm introducing these words to you so that when you hear them in the future, they'll be a little less scary. And you'll say, oh, yeah, I heard something about that before. I didn't really understand it then, but at least I know that this is an idea and maybe I can get better at it next time. So this is just the first introduction. Uh, don't like get in your head too much about this if you feel like it's confusing. Now that I've set the stage, an active transformation and a passive transformation are two different perspectives on what a transformation can be. An active transformation takes an object in the space and transforms it relative to the coordinates. So that would be like in the triangle example from the previous video, I performed an active transformation on that triangle. The coordinates stayed the same and the triangle became transformed. But there's a mathematically equivalent way of thinking about these things, which is the idea of transforming the coordinates and leaving the objects in that space alone. This means that the coordinate values of that object in the space change. And I must be allergic to this stuff. It's still painful. Okay. We're not going to edit that out. All right. So passive transformation is transforming your coordinate axes. This means that the coordinate values, like the x and y and z numbers that you attach to objects in this space, those will be different, but it's not because the object transformed, it's because the coordinates transformed around the object. And so its position relative to the coordinate axes has changed. I'm not going to say more about that. I just wanted to put that out there and you can think about it. And then in the future, if it turns out you actually need this, then you'll be in a little bit better place to work with it. Okay. I said this in words before, so I just want to put it in writing with a reminder that order of multiplication matters with matrices, except for the identity. That's our number one. It can move around anywhere. So any transformation can be written as a combination of simple transformations acting in sequence. possibly including a translation somewhere in there as well. So once you know how to write scaling matrices, shearing matrices, rotation matrices, reflection matrices, then you can make whatever complicated operations you want by saying this one times that, times that, times that, acting on my vector or acting on points in the space tells me how those points transform under this action. For example, we're going to take this location in 3 dimensions, 1, 1, 0. So this is in the xy plane, right 1 over 1, and then it is at a height of 0. We're going to rotate it around the x-axis. We are going to scale it upward by a factor of 3, or scale it outward, really. Then we're going to take that and rotate it 90 degrees around the y-axis and ask, where does it go? So again, 1, 1, 0, 180 degrees around the x, triple scaling, 90 degrees around y. There's 2 different ways to approach this problem. One is to sit down and think about it and draw pictures. Drawing pictures with these problems can be so helpful for checking your work, for making sure things are making sense, that they're behaving the way they're supposed to. So if I draw my coordinates x, y, z, so I had my point 1, 1, 0. And then I rotated it around the x-axis. I said this out loud, but x, y, and z. All right, so it goes 180 degrees around the x-axis, and it lands over here. And then that point's distance from the origin is going to get tripled. So it's going to go wee out here. And then that thing is going to rotate 90 degrees around the y-axis. So here's our new point. I have to extend my y-axis outward. And then this is where you got to be really careful with directions of things. This is a positive angle, so it's anti-clockwise around the y-axis. So I'm gonna, again, I wish you could see this, but I'm not green screening it. Put my thumb on the positive y-axis and then rotate my right hand 90 degrees around to see which way it goes. And so it goes down this way. Drawing in 3 dimensions is just so hard on a 2D surface. Masters of perspective can do it. That is something I am not. All right, so our final point should end up somewhere down here. That's the think about it method. And at the end of the day, let's see, what would this have been? So this would have been x equals 1, y equals -1, z equals 0, and then it would have been tripled. So that would have been 3, -3, 0, and then finally we would have rotated it 90 degrees down here. And so then it would become, oh boy, I had it. So the x would be 0, and then it would be at -3z, and it would be at -3y. I think. All right. Now, doing this with pictures is great if you're good at drawing. I very clearly am not, and so I just do this stuff by math. To be very honest, 3D visualization is very difficult for me. I've always struggled with it. This might sound like a silly example, but I actually mean it. I do not understand knitting at all. I think it's very interesting. I think the things that people make with yarn are very impressive, and like, I just can't do it in my head, like to try to see how yarn moves around and like how different loops and knots get formed and how they're stable, and like I can't picture it. It's just a difficulty that I have, but I'm real good at multiplying matrices together. So I personally do these problems with the algebra and let the numbers take care of me. I'm not recommending that for everyone. If you have good visualization skills, you can do a lot of this geometrically with your imagination. So they're both valid approaches. I'm going to multiply some matrices now and get back in my comfort zone. All right. So here's my rotation around the x-axis. I put in my 180-degree angle for theta, and so I get -1, 0, 0, -1 with theta equals pi. Here is my tripling. I called it T for triple, very clever. And this is a pure scaling. Everything just gets 3 times bigger, so it's 3 times the identity matrix. And then I'll have a rotation around the y-axis. Notice that the SIGNs, the positives and negatives of the SINs, have flipped. God, I wish we could pronounce those things differently. Let's start a revolution, you guys. We're going to start calling it sign instead of sign. We'll see if that sticks. All right. Anyway, so I put in my 90 degrees here, and then I get 0, 1, -1, and 0 with that 90-degree angle. So now I have my 3 transformation matrices, and the whole compound transformation is made by multiplying these. So I do all the multiplication and multiply the first one times the second one times the third one in that order, going from left to right. And then I get this final result. So that is the transformation matrix itself. How does that transform the original point? Now I applied that matrix to the coordinate vector that I started with. And it looks like I almost did this right in my head when I was trying to do the drawing version. It looks like I flipped a sign and SIGN somewhere. But, I feel like it's important to be honest about things that are hard for us because not everyone is great at everything, and that's okay. That's why we work in teams, right? So we can work with people who are different from us and who are good at things that we struggle with, and as a whole, we succeed together. Okay, anyway, this is the final coordinates of our transformed location under this compound transformation. Now, in the most general case, looking beyond just rotations, you can have any elements anywhere in this matrix, and you do the matrix multiplication, and it's like the matrix multiplication that we saw previously. I could say more about that, and I did say ahead of time this video would be longer. It is longer, and that means it's time to stop. So I'll just say that this will come back. We'll revisit it later in some other contexts and get some more appreciation for what's going on and understanding transformations in terms of matrix elements. That's it for now. Thanks for sticking around. Every once in a while, a topic just needs a longer video because there's that much to it. And I know people do want to see more examples, and examples take time. But, that's how it is. So with that, I think it's time to wrap this up. I'm really excited for the next topic. It's just one of my absolute favorites. Maybe in all of math, to be honest. So, yeah, with that, I'll see you next time.